The next step is to look at covariances. I think you've seen this before. So the covariance between, at least most of you have, between two random variables, x1 and x2, is defined as the expectation of the product of the central deviation from their expectations. So it's the expectation of x1 minus its expectation times x2 minus its expectation. Similar to the calculation we did just down here, you can do the same thing and you end up having that can be calculated as the expectation of the product of the two minus the product of the expectations. Okay, and as a special case, the variance is the covariance with yourself. We're still in univariate case. A nice calculation rule for the covariance here. This is kind of what makes you not have to do all the integrals. Just remember this one, then you can go through almost everything. Basically, consider it, as we did up here, as just two products with expectations. So that means you have to take the product of this with that and do the expectation of that. That means that what you have to do is to take the first element with the first element, the first element with the second element with first, and second with second. That is exactly what we have down here. And all the constants here are just moved outside. So that's the calculation rule. It's pretty much just the same thing. You take two parentheses and multiply together. And then constants outside. That's what the rule is, but it's going to be handy. Let me put it that way. And of course, the same thing applies to the variance. As it holds up there, it of course also holds down here. So the variance of anything here, you plug that through that. The variance of a constant is 0. We leave it out. Then we have b times a random variable here. Well, then we have from both one for the first part and the second part here, we get a b, so we get a b square. In the univariate case, we don't have to do the transpose. So basically, life is easy. Now, if you see the term a second order moment representation, for instance, then what you have to do is not just to do the second order moment, but you also have to do all the moments up to the second order. So you have to do, to represent everything up to the second order, you need the first order and the second order. And the second order is, part of it is the variance, and if it is a multivariate setting, also the covariance. So that's that small thing. Now, we'll just take and do everything. Oh, have something sitting. If you look at a vector, of random vector here, then we do the expectation is basically, it's just the element-wise expectation. So that's an easy one. And the covariance matrix, here we have to make sure that we get dimensions right. So we have to obey the rules of linear algebra. So basically it's the same thing here, that we have the x minus the expectation of x square. But what is the square of a vector? There are two ways you can do that. You have the inner or the outer product. Here, what we want is the outer product that we have here, because then we get to get the covariance matrix between the two, between all elements. I'll get back to that on a subsequent slide, or no, it comes there. So in the diagonal here, what we have are the variance of the different elements of the random vector. In the off-diagonal elements, we have all the covariance, all the pairs of covariances there. And notice here the covariance of x2, x1, and the covariance of x1 and x2. They're equal. So in order to have a covariance matrix, it has to be symmetric. So that may become handy at some point. Correlation is, as always, the covariance divided by the square root of the product of the two variances. It's the same definition we have here. I will sometimes use the notation here. When you have a covariance estimate here, then you have sigma and then two subscripts. Then it's the corresponding element. If you have it only with one subscript, then it's a standard deviation. Then it's a sigma. Whereas we have two subscripts, it's a sigma square. Does that make sense? So sigma I is a variance. Sigma I is just the standard deviation. So sometimes you will see with double i's or double j's, and then you take the square root. So that expression there is equivalent sigma I j over sigma I sigma j is equal to sigma I j divided by the square root of sigma I multiplied by sigma j. So that's just notation that sigma I is equal to the square root of sigma I. Getting back to independence, well, now we have correlation as well. So if x and y are independent stochastic variables, then the covariance is 0. And of course, if the covariance is 0, then the correlation is also 0. But we can construct examples. Say, if you have x being a standard normal, and look at the covariance between x and x squared, we can do the math. That becomes the product of that. They have expectation 0, so we remove those terms there. Oh, sorry, and then you have minus these products here, but that number there is 0. Expectation of x is 0. So that term there goes out. We're left with this term, and then we just have to calculate the third order moment. And for normal distribution, that is 0. Now, that means that x and x squared are uncorrelated, but the conditional expectation of x squared given a value for the other one is not 0. Yes?
Is there some intuitive explanation of the third moment?
It's called skewness. Skewness. So it's are the tails of equal weight. So independence implies correlation, but not the other way around. That's the take-home part. Now, we will generally work in a case where we don't do nasty stuff like this, but it's important to just keep in mind that when you have a nonlinear relation between two variables, they may not have any covariance or be correlated, but they're not independent. But it takes the nonlinear relationship. Now, if we have two vectors x and y, well, sorry, the correlation matrix is basically just taking all the elements here and putting those into matrix. I think that's just want to have it stated. But now, if you take the covariance matrix between a random variable x, a vector, and another variable that may be a vector y with different dimensions, the definition is the same. It's the outer product of the two. And then you have all the pairwise covariances between the different elements of the two vectors in that matrix that comes out. And you can say calculation rules are same as when you just look at the variance. It's just yet another generalization. So, and of course, the variance is a subcase again. And here is also where we have what I just used before. By intuition, if you take a constant matrix, multiply that on a random vector here, the variance of that is that constant pre-multiply and post-multiply transpose on the variance of x. This slide is represented as a table in the book. I forgot what the page number is. These are some of the calculation rules for expectations that will make your life easy if you remember them. First, let's try to understand them a little bit. The first one is just the definition of conditional expectation. It's the conditional density that you use to calculate the expectation of y. That's the definition. So I think mentally that's fairly straightforward. Some of the others are very intuitive, and some of them takes a little bit of thinking. So if x and y are independent, then the expectation of y given information about x is just the expectation of y. Okay, that one, we're happy. If you take the expectation of something that is totally independent of something else, whatever that something else is, it doesn't matter. Second one, this is one of the things that you have to think of. What is actually the meaning of this? The expectation of y given x here. So then that is a function. Look at what you have up here. We don't give a value for x. So it becomes a random variable where x is the random part. We take the expectation of y given a value of x, but we haven't specified what x is. That is still a random variable. But now we can take yet another expectation of that random variable, and then we just get the expectation of y. Now we can go a little bit further than this. If you take the expectation of a function of x and part of y, given information about x, well, x is a random variable, so given x, then g of x is a constant. We can take constant outside. So any function there, but it's still a random variable, and that's, I think, the mind-boggling part of this is when you conditional a random variable, what you get out is when you do the expectation there, you still have a random variable. The expectation of g of x times y, here you can do kind of the reverse of what we have up here. We can kind of introduce an expectation, basically doing what we have up here. We can insert this in here. So what this means is, if it is easy to say something about y when we know x, then this can help us in doing the calculations. And then we're left with only x as a random variable in the inner part in here. The expectation of a constant given a random variable, well, the expectation of a constant is always a constant. The expectation of a function of a random variable given that random variable, well, it's still a random variable, and it's just that function. That's basically what we used up here to move g of x outside. And last but not least, it's the linearity of the expectation operator. It also goes for the conditional expectation. So when we have the expectation of a sum of things, we can take the sum of the expectations instead. I think that's also straightforward. So there's a couple of them where you will kind of have to spend a little bit of time to figure out what is actually the meaning of that and when can I use it. I'll promise you'll get to use all of them. At least if you want to pass. So another thing is variance separation. So definition, conditional expectation, conditional variance here is the same thing. The definition of the variance is the same as before. The only thing is that everywhere where you have the expectation in here, you have to have the condition on x here, there, and there. And for the covariance, you can see it's the exact same thing. The only difference between that is that the set here comes in 2 places there and replaces the y. But the structure is exactly the same as before. It's just that when you do the conditional variance and covariance, everywhere where it just had an expectation before, you have to have the conditional expectation. That's what it is. Now, if we combine this with things on the previous slide and do the math, this is one of the things, again, why do we want to have these calculation rules? You'll see later. So the variance of y, you can split that into a sum of 2 elements. It's the expectation of the variance of the conditional variance of y given x plus the variance of the conditional expectation of y given x. So why at all consider doing things more complicated? Well, because sometimes in reality, you know that something depends on something else. You're interested in the variance of this, but there's dependence on this other thing. And if you know this other thing, this relation is easy. But then you have to make sure that you don't just take one of these terms, but you take both. Because you have to take the variance of the conditional variance of the link between the two. You have to take that, and you also have to take the variance that comes directly from x. And the similar things can be done for the covariance, that you have a similar structure. The covariance of y comma z is equal to the expectation of the conditional covariance of y comma z conditional on x plus the covariance of the conditional expectation of y given x comma the conditional expectation of z given x. There's too many words to say in that sentence. It's easy to read, I hope at least. But the underlying thing is, if there is some underlying stochastic variable x that can make calculations easier, often it helps to separate the variance in this way. So linear projections, you've all done this, but just not in this way. I'm not 100% confident, but I'm somewhat confident. You've all done linear regression. It's not quite the same thing, but it's quite similar still. So if you have 2 random vectors, they may be just scalars as vectors of length 1. Now, they have a mean value structure and they have a variance structure and covariance. So you have the variance of y and the variance of x and the covariance both ways. So, first of all, just a small side question. What is the dependence between sigma, what is the relation between sigma xy and sigma yx? Yes? Sorry? It's the same, yes, if x and y are univariate. If they are multivariate, it's not the same number. They are exactly each other's transpose, because otherwise you could say the joint covariance matrix here is not symmetric. So that's just to keep that in mind. Now, the linear projection theorem, rho of, we take y and project that on x, is take the mean value of y, and then you take the covariance matrix between y and x, and then you normalize it by the inverse variance of x, and then you look at how far you're away from the mean value of x. That is basically what it is. There's a drawing in the book where basically this is in the n-dimensional case. Basically what you do is that you figure out x spans a plane and y is another plane, and then you look at how is, when you take y and project that into x, where does that belong? So what happens here is it becomes the structure of a linear regression, y equals a plus bx plus some noise. Now the difference here is in which direction you do the optimization. When you look at a linear regression, I'll just do, this is one of the easy ones, right? There's a linear relation there. What is the assumption about uncertainty here? What is the variance of the x's down here? When you fit this linear regression model, what you do is that you minimize the vertical sum of squares. Only look at the vertical errors, right? Now, that is because you assume that the x here is given. So there's no uncertainty in the x. You observe the exact value with no noise, no whatsoever. I mean, how many of you have done things in practice? Does that always hold? Sometimes it's a good assumption. But you may argue sometimes that if you have an uncertainty on stuff on a point down here, and then you also have some uncertainty over here, maybe the appropriate thing for that point that is out there is not to do the vertical, but to do some kind of another distance to the line. And that is exactly what this is doing. It's looking at the correlation between the two and looking at the variance of x. So it finds a direction where you kind of look at the variance of the two and use that to say, how do I want to minimize things? So rather than getting the point that is just below, you get to a point that is on the line, but reflecting the uncertainties of the two. In the case where the uncertainty on x is very small, and the uncertainty y is great, then it will actually become the vertical in the limit. Okay. So one of the things here is we look at the variance structure of what is the variance of y minus this projection down on x. It's the variance of y minus something here. I won't prove that one. What I will consider is looking at the covariance between y and the projection. How is that related to x? I want to show that it is independent, just to make sure that I don't make too many typos. So if we look at the covariance of y minus rho x of y, comma x, what do we get? First, let's just plug in the projection here. So we have the covariance of y minus what we have up there, mu y, then we should have a minus here to avoid the parentheses, sigma y x, sigma x x inverse, x minus mu x like that, and then comma x from over there. So what do we do now? Here we just have some terms. Let's just look at them and see what does actually give a contribution. This is a constant. What does it do to the covariance? Nothing. There's yet another constant there. So let's just start by trimming down to those elements that actually give a contribution. So we had the random variable y minus sigma, that's a y and an x. Yes, sigma x inverse on x, and then comma x. So that's what we have. So now we can use the function from before, and we just do, you say, all the pairwise covariances that we have to do. We have two elements here and only one element over there. So we take the covariance of y with x, minus, then we have some constants here. Those we can move outside. Sigma yx, sigma xx inverse, and then what is left is then the covariance between x and x. Now let's look at the individual terms here. What do we have? The covariance between y and x. Well, that is what we define as sigma yx minus sigma yx, sigma xx inverse, and the covariance between x and x, that is exactly sigma xx. Now, sigma xx inverse pre-multiplied on sigma xx, what is that? That's the identity matrix. So what we have left is sigma yx minus sigma yx. Well, a minus a equals 0. Done. So that was the first use of one of the helpful calculation rules. Now, we often kind of relate this projection to the conditional expectation. This is not always, so I'll write it with a. Sometimes it holds that this is the conditional expectation of y given x. Doesn't hold always. Using the same case as previously with x squared and x, because of the nonlinearity, it breaks down. But if things are linear, it holds. Well, linear projections, there's something about linearity that kind of goes into the wording there as well. And that's also the reason why we have stuff here. So the projection there is minimizing the variance among functions that gives projection errors that are uncorrelated with x. So that's kind of the background story. So we've proven the non-correlation here. So if x and y are multivariate normal, then that is actually the same thing for the conditional expectation. So the conditional expectation minimizes the variance among linear functions that gives you uncorrelated projection errors. So in this case, where you have x squared, that's 1, but the conditional expectation is x squared. Of course, that in that case doesn't hold, but that's, as said before, due to the nonlinearity. So we will, however, use the conditional expectation for the linear projection pretty much everywhere, but just be careful when we use it. Because, well, we do it, the book does it, everyone else does, but just keep in mind that there may be a difference in some cases. So at the end here, an example of air pollution, measurements from Copenhagen, Jagtvej. I don't know how many of you have been there. It's not that much place for bikes, been there many times. So here's the old data where they only measured every third hour, now they measure every hour. They have some mean values for the NO2 and NO, and the sum of that is what's called NOx. I don't know if I say Dieselgate, if that reflects something. So then what we define is, we define one random variable x1 as the deviation from the observation of NO2 to its mean value, and reverse, and likewise for the nitric oxide, we define that as x2. And why that order, I'll show you later. So someone then came up with this model. You'll learn how to do that later, but let's just assume that we have this model. So to get from a time point to the next time point, we have this matrix to multiply with. So we get roughly the same as before, a little bit less, but then there is a link between the two. That is actually also the truth, because they do, there is a chemical balance between the two forms linked to ozone as well. Just have to find the English word. And then plus some noise. We can have it on a simple form like this. We can have the covariance structure for the residuals up there for the noise was estimated to be these values. And let's just assume that t corresponds to now, 9 o'clock today, and what we observed were those two observations there. So now the task is, how do we make a prediction at noon? One step forward in time. And what is then the variance covariance of that forecast error? So to get the prediction is fairly simple. We just have to remember the best predictor is the conditional expectation. And we just observed what it is, those two values. So what should we do with this fellow up here? We should progress forward in time, one step. This is noon. This is, we have the values at 9 o'clock. Those are given. So this here is a constant. That out there is a random variable with zero mean. So the conditional expectation of the right-hand side there is just this constant here when you multiply it out. So what is then the variance, covariance matrix of that forecast error? Well, since this part here is given, there's only one noisy term that is out there. And since we do not multiply anything to it or anything to it, well, we have it right there. That is what comes here. A little bit more steps. So we do the conditional expectation, and it's just the, you can say, deterministic part, because we knew xt in this case. And we don't know anything about noise in the future. And for the variance covariance matrix, well, then we have to look at the variance of xt plus 1 minus the conditional expectation, that conditional thing there. Well, then we have the true value in the future is this parameter matrix phi here times xt plus the future noise minus the conditional expectation that we have here that we just calculated from there, and then we condition on xt. And then we see that phi xt that cancel out, and we're left with the residual. So we can also do the calculations based on what we did before to just get sigma. Now, I won't go through this, just leave it there. You have the slides. So those are the values, 61 and 96.6. After adding the mean values again, that's what we get out. So maybe it's just for reference, I'll just write those numbers down here. 61, 96.6. Now, at noon, what happened was that they did observe the first date, NO2, to 67 as a result, but they did not measure the nitrogen oxide due to some measurement error. That's just life. Any one of you who have worked with real data, real sampling things, there's always sometimes happen. Some things will happen. Loss of power, loss of something. Someone made a bug in the code. I think we've all been there. So now, what can we say about the estimate right now for the one that we did not observe? What can we say about it? This is, I know, a lot of characters on one slide, more than I prefer. So what is happening? What we are asked to do is to look at the conditional expectation of x2, which is the one that is missing, given the one that we observed at noon and the previous observation. So far, so good. Then we do the linear projection theorem. We have it down here as a helper. So what we need to do is then to first have the mean value of this. That's the mind-boggling part here comes from, we always have to condition on xt as well. So where we over here just have the expectation of y, it becomes the expectation of x2 at time t plus 1 given information at xt. So we have an extra conditional thing there. But that is the expectation of x2. Plus, and then we have the covariance between conditional covariance between x1 and x2, pre-multiplied on the inverse of the variance of x1, conditional on xt. And then how far is the departure of the observed x1 from the expected value of x1 that we have there. So that is what we have up there. And the next line is basically just plugging in coefficients for everything. So this here is the expectation here, the covariance between x1 and x2 given xt. That's just the element 1, 2 in the covariance matrix. The variance of here, x1, we saw that that's just the variance of x. We have their inverse. And then we have the observation minus the prediction of that. Now, these values were back on the scale where we added the mean value, so we cannot directly compare, but right now. So that is what it turns out to be. And then we need to look at the variance of that. And we end up with this small thing here. So the variance of the projection error, if we go back some slides, where was that? The variance of the projection error is given here. It's the variance of y minus sigma yx on the variance of x inverse sigma yx transpose. So it's the variance of what we have minus the covariance. In this case, it's a scalar. So I don't have to pre-multiply by the covariance and post-multiply by the transpose. I can just take the covariance of x2 and x1 square in front and then normalize by the variance of x. So that's what we have. So what is the interpretation of this? We have the one-step prediction variance here, sigma 2,2. We reduce it with something that comes from the correlation or covariance structure between the two different states, normalized by how much information do we have in X. So the larger the correlation between the two, the more information, the larger reduction they have in variance. And the smaller the uncertainty is on the first state observation error, the more information you have. And if we do the math, then our updated prediction is 102.9. So it is an update from what we predicted before. The variance before and now is 0.95. And we'll have to go back a few slides. I can see the number is 23 there. That's the matrix. I also have that on the... Oh. I have to go how far back? There. That's the covariance matrix. So that's the variance for the second element there. So it's a large reduction in variance because there's a large large reduction in variance because there's a large covariance between the two states in this case. So what we've covered today from a random variable point of view, besides an introduction to the course, this covariance calculation rule, we already used it a little bit, the variance separation theorem, and then a linear projection, and then just saying whenever you want to represent things with moments up to, then it's up to that order. So that was what I wanted to cover for this part, but I think what I want to do now is just to log in to learn, to see how things works. I have, how should I say it, cheated a little bit. Sometimes it's allowed to cheat. Whenever you haven't been logged in for a while, it will kind of pop up this window, and if you just say that you want to log in, then it will kind of stay where you were before. This is a separate student that I borrowed from the administration because we are in the testing phase of things. Yeah, you can see the name. Anyways, there are a few of those students out here that you won't meet out in real life, but that's another story. So this is what you see when you log in to learn. What I've tried to do is to have a calendar out here where for every week, I just say that there's one deadline Friday morning. I can give you a deadline for every single task and every single element, but I think that will just be too much noise. So I'll say that this is what I expect you to have looked at before Friday mornings. Now, what you can do is to go into this is the first element. It was this morning. Then you go into which tasks are there for today. Here says what is the reading for today. And then I've uploaded the slides and I made a small quiz. And I want you to test that conditional expectation quiz there. And then I made a list of exercises. So that's one way to get in here. Another way to get in, if you go back to the front page, and I think that's kind of the more organized way to get in here. If you go to content at the top there, then you can see what I have put in here. I haven't made a nice overview yet. That may be coming. Basically saying what's happening. But what I've done is that I've made it for each week I've added what you are expected to do. And if you look at week 1, it is exactly the same thing as you saw just before. So here you can download the slides for today. Here you have a quiz. And here you have which are the exercises for today. So, and the quiz here, just hit start quiz. And I'll just pick a random answer. And I'll submit this quiz, and yes, I will. And then that was it. To navigate between the different tasks here, you can also navigate up here. There's the exercise, the quiz, and here is the place where you can download and actually see the slides inline here, if you like. So you don't have to download them. So that's for the first week. Now, from the time onward from here, this course is going to run a so-called flipped classroom. So I don't know how many of you have done that before. A few. So what is happening if you go back to content for next week? Everything is ready for next week. I'm almost done with week 3, but I had to do some testing that I couldn't do until during this week before I kind of set things up. So this particular user already tried the quiz for next week. What you will see in here is that I'll just collapse everything first. I planned for every week to have what is the expected reading at the top. Then I have some podcasts. Then I have, you can say, slides. And whenever there's some code that is being used in the slides, I will upload that code so you have the R code that I've used. And then what are the exercises for that particular day? I don't expect you to have solved the exercise before we meet, but I mean, if you looked at it, it's great. So for the podcast part here, what is here is that I took the lecture, and this particular lecture I broke it down into 4 parts. You will notice one thing, that when I give the lecture in the video recording studio, I use less time for various things. So there may be places where you want to kind of rewind and see things again, just to get what was actually the meaning of that. But I've recorded almost all lectures shortly after I gave the similar lecture. So I try to remember what are the questions and trying to answer those questions when I give it again. But they are not that long. They are roughly 10 minutes each. There are some that are shorter and some that are longer. The longest ones are typically examples where I show some R code and I don't want to chop that into pieces. But then, I mean, take a break whenever you need it. After each video, I've added a small quiz. Some of the first ones are so-called self-assessments instead of quizzes. Then Learning Lab said, well, do use quizzes. It's the same kind of questions in there. It's quite flexible with regards to which kind of questions I can make. But I'll try to make some mostly multiple choice, some multiple select, some maybe others. Those quizzes, it looks very formal the way that you kind of click into it. You have to approve, yes, I want to try it. I think I did not fix it everywhere, but I want to say that everywhere you should have an unlimited number of attempts. It doesn't go into grades as such, but it's just for yourself to kind of check, okay, did I actually get some of these things happening here? And for now, my ambition is to say, I want to have 1 question after each video. So it's a quiz with 1 question. It's not a long quiz. And I set the time to be, I expect you to use a minute to do that. So it's not something that should be complicated and take a lot of time. So it's meant to be kind of a help to say, what was at least one thing that Lasse found important in that part? I can make more. Oh yeah, that's whatever. I can make more questions in each of them. Maybe I should, but it's also a matter of how do we do things. It's one of those things, the number of questions and how to use this setup I would like to have a lot of feedback from you guys during the semester. I don't want to just do a midterm and then you say everything was just bad the way it is. I want to adopt. That's also why I will make sure that before next week 3 is done, probably week 4 is also, but then I will kind of be doing a rolling window throughout the semester, so that things that we want to adopt, let's try to see what we can change. Pretty much everything is recorded, so that's the difficult part. But I'm quite confident in that part as well. So, any questions, immediate questions to this? So the way it's going to work, and I think I wrote that in the message as well, is that rather than giving a lecture every Friday morning, you have seen this before you come, and then we'll start at 9 o'clock. For now, see how that kind of matches time. That leaves us time to discuss the difficult parts. And I think one of the nice things about flipped classroom is that we can spend more time on the difficult parts and less time on the easier parts. And it's, of course, individually what is difficult, what is easy. You also have, under activities here, discussions. Right now, I just have, you can say, a discussion thread for how to use Learn. If you have questions, comments, feedback, whatever, add a thread there. I don't have much experience with this discussion forum yet. Hopefully we will get it. I will create kind of a forum for each of the assignments that will come later on in the course, so that it's easy for you to figure out if I have questions related to this, this is where to look. If someone else already asked and got an answer for that question. Now, in Learn, there's one thing that is important. That is announcement. If I send out a message, if there is something that is sent from Learn, right now the default is that you have to log in to see them. But in your settings, notification settings there, then you can change which kind of notifications you want to have as email and when do you want them. And you can customize it quite a bit. Personally, I have to set right now to have a daily summary of activities just to get something, but I will change so that announcements to have those as emails when they come, because those are probably the ones that you want to use. But I mean, there are many different things that you can get. I won't use this for grading, even though there's something about grading in there. I will use what is called peer grading, but we'll get back to that in detail when we get closer to the assignments. There's one asking, when are these assignments due? I will update the calendar in here so they are visible somewhere and show you where they are. There will be 4, and you will have 2 to 3 weeks to work on them from it's handed out to the deadline. And the last one is by the end of the semester. Sometimes the last deadline is pushed a little bit into the exam period. Let's discuss that when we get to that. It's not relevant right now, I think. I'm reasonably flexible as long as we can make everything work out. So good arguments, I listen to those. Is there anything else I need to say about Learn? When you first log in, how to get to Learn. I mean, I wrote what you can do. Now, let me change and be myself for a second. So when I go into this course, and if you just scroll down a little bit, then there's a link down here, Go to Learn. You can also just type learn.insight.dtu.dk. So, depending on whether you are a typing man or a clicking person, various people had various differences, preferences there. So, could I ask you to just, at least before you leave, go in and test the quiz in there, just so that we know that everything is working. If you have questions, say so, and then we'll take it from there. Are there other general questions? Yes?
How many assignments?
Four assignments. I think the first one will be released in a couple of weeks. But we'll need to cover a little bit of ground before it makes sense to get to hand it out. Yes, but what I plan on doing. First of all, I will add them to the calendar here when they are due. But I will show those dates already now. But I won't handle them in there. And the formal thing is, it's always these things about new systems. It's a technical thing that when you hand in an assignment, we have to archive those assignments for a year. And I asked, well, does this system provide that service, or do we have to use the inside system to do that? Because there it is archived in an appropriate way. Alternatively, I have to do it manually. And I just like to have things, if you can push formal things off to the system, that's a preference. Then you know that things are done the way it should be done. So until I get the confirmation that, yes, it can do that, then we'll do it this way. Yes?
Turns out this banner, learn banner, is absent for. So your clicking banner should be.
Let me just see.
So if you're looking at the student, there is no banner to go.
No, if you go into the course.
Oh, okay. Then that's me. Sorry.
There.
Yeah.
There.
There it is. All right. Right.
I think I did something that should be foolproof. Okay, if there's no further questions, then let's discuss it on the fly. Yes?
Do we get instant feedback on the quizzes, or is that first a bit evaluated next day? You don't get answer if you answer correct on the quizzes or not?
I will. So that's one of the things I have to look into. I want you to be able to see the instantly. So let me tweak that. I'll play with that right now.